We are here today to talk about Bloop. Bloop is a project that we have been developing at the Scala Center for the past 5 months. It is mainly focused on developer ergonomics and developer productivity. So this talk here is going to be about how you can use Bloop to be more productive. And the logo here, or killer whale in the screen, is our logo. It is, well, killer whales are beautiful animals. They are also powerful and fast enough that they can go after sharks and just kill them. So that's what we wanted to achieve with Bloop. And we wanted to be beautiful. We wanted to be fast as well. So that's why we used a killer whale as our logo. My name is Jorge. I am a developer. I work on developer productivity at the Scala Center. I've been working there for the past 2.5 years. I'm mostly obsessed about developer productivity, and all my work focuses around that. So I co-maintain Scala's incremental compiler, Zinc. I work on build tools, build servers, and anything that has the build word in it. And I've also been doing some work on Scala C, Scala 2's compiler plugins, and infrastructure.
My name is Marta. I've been a software engineer at the Scala Center since March 2017, and I'm working only on compilers and build tools. Previously, I was working on SBT, I was also working on Zinc, I've moved to Scala Native, and now I'm working on Dotty. One of the things that I've been bothered with is that sometimes I feel like tools are getting in my way. They try to force me to work in a way that is not best for my workflow. So that's something that I've been trying to improve, and I've been focused somehow on how to make tools that are completely agnostic of the build tool. I would like to start the presentation with one code that we got on our GitHub channel for Bloop. It's the report from a user of Bloop who is pretty happy because they have a large project that is built on its libraries built on top of libraries and so on and so forth until they reach the top where they have customer plugins that they deliver. And whenever they make change at the root of the project, they have to republish all the different layers of libraries that they have, and it takes them tens of minutes to be able to see the changes that they've done at the bottom of the project. They have to wait tens of minutes to see the changes that they've done at the bottom, at the top. So they've been using Bloop and developing more tooling on top of Bloop so that they could reach seconds of turnarounds instead of tens of minutes. So with that in mind, we've been trying to write tools that are flexible enough so that you can adapt them to your workflow. And those tools, they should not try to force you to adopt their vision of how you should be doing the work that you want to do. And that's what we wanted to achieve with Bloop.
So now we're going to mainly focus on how Bloop can make you more productive. But before we dive into the details, we have to explain what productivity means. The way I'm going to use productive in this talk is by just basically defining productive as I am productive when I carry out a task, and that task is bound by my thinking process and not by the tools I use. That means that I am allowed to, wait for 2 minutes and just think about how I'm going to solve a problem, but I shouldn't be waiting 2 minutes just to SBT to finish the compilation of the changes I just did, right? So the goal here is to minimize the amount of time it passes between a change in your editor, a change in the code, and an execution result. That execution result can be a compilation result, can be a test result if you are testing one or several tests, right? And what Bloop tries to do is to minimize the amount of time. So this painting is called the Zoo of Build Tools. And you're probably familiar with it because you've seen it in your nightmares, or at least I do. Build tools are very peculiar. They are beasts that have lots of different properties, and they are very different from each other as well. Here we have the most popular build tools in the JVM and Scala community. We have Pants, Bazel, SBT, Gradle, and Maven, right? And essentially build tools are so complex, and they have to carry out so many tasks that users of them are usually not very happy with them. So what we wanted to do with Bloop is to try to create something we could be proud of, something that was beautiful, slim, that we could easily integrate with anything we wanted. So therefore, we ended up with this. So this is essentially Bloop. It's a mythical creature, it's a faun, and It is beautiful, it is fast, and it is actually our unofficial logo. Heather doesn't know about it yet. But we want you to picture Bloop as this fun and not as this beast, right? So you can think of Bloop as a Sync++. Sync is a Scala incremental compiler. So what we've done is we've added several layers on top of it to provide a lot of functionality that we'll be talking about in the next slides. So when you look at the tools we use as developers, especially from my point of view, there are basically two kind of, like there's a very white and black situation. There are no scales, there is no gray in the picture. And on the one side we have Scala-C, the compiler, right, when we want to compile code. And on the other side we have build tools. The problem with the compiler is that it doesn't give us any kind of code compilation. It just compiles our code. It's a CLI tool. It doesn't give us any kind of incrementality. So if we want to change our code and just recompile the things that we change, that doesn't work. And it doesn't know in which context it's used. And that means that there are lots of performance opportunities that are missed just because we cannot leverage the information that the build tool has. On the other hand, we have build tools, and the build tools are the end of the world. They are the interface that developers use to get their job done. They are unfortunately too heavyweight, as we said before, and they are difficult to integrate with. So what there is, like the gap we want to fill in here has to basically try to make a compromise between these two different tools that we have and we use today. It has to complement with whatever build tool you are using, right? It has to compile the code, and it has to be as well incremental and fast. But it also needs to be extensible. It needs to adapt to the kind of workflow you have, no matter what it is. Because in reality, developer workflows are a product of the social circumstances in your company or in your project or in your team, and depend very much on the culture of it. So it doesn't really make sense that the developer workflow is tied to a build tool. A build tool should, like, if you want to compile your code, that should not have anything to do with the build tool you're using. So what can we do here? What we can do is we can create centralization. We can create one server that will compile all the programs we want. And we can get all the build tools around it to use this server in the background. This has many, many benefits. The first one is that the changes to this code base will have higher impact. It will be easier to maintain, easier to optimize, and easier to test. And this is especially important when we, compiler developers and tooling developers, try to improve the compilation performance of the compiler, or trying to improve the developer ergonomics of it, so that you can instantly benefit from it by just depending on the artifact we publish. And most importantly, it needs to remove the fragmentation that there is in build tools. I don't know if you're aware, but people that use Scala and Gradle, for instance, are still depending on an incremental Scala version of the incremental compiler that was released 3 years ago. That means that the productivity is heavily hurt by the lack of, by the fact that they cannot use the latest changes that have gone into Zinc, particularly particularly Zinc 1 that was heavily improved to provide better incremental compilation. Therefore, Gradle users that do Scala have a poor developer experience, and that's what we want to fix.
So now let's see a bit more about this compilation server that we want to introduce. This is a picture of the architecture of the tools that we have today. First, you have your IDE, which to provide you with the highlighting and show you errors in the code, it has to depend on one instance of the compiler. You also have your build tool that you're going to use, for instance, to run your test, which also needs to produce class files to run the test, so it needs an instance of the compiler. Finally, you also have other tools that you use. For instance, you could be running some refactorings of your code, and for that you also need one instance of the compiler. So you have 3 different instances of the compiler. All those tools need to integrate with the compiler, and nothing is shared. What we propose instead today with Bloop is that all those tools could benefit from one integration with Bloop and delegate the task of talking with the compiler to Bloop, so that they don't have to all re-implement one integration with the compiler. They just have to have one integration with Bloop. Doing it this way has several nice properties. First, this means that the integration that they have to do to be able to talk to the compiler is completely compiler agnostic. They don't have to care about supporting Scala 2 or Scala 3. They can just benefit from the integration that Bloop has today, which is able to work both with Scala 2 and Scala 3, which is coming soon. So it removes a lot of complexity from those tools. Moreover, today we're not only running Scala on the JVM. We also have Scala JS, which is close to 1.0, and Scala Native, which is progressing very fast. Bloop is able today to link projects with Scala JS and Scala Native, and the other tools that would need a compiler, that would need also integration to work with Scala JS and Scala Native, would all again have to redo the work that already has been done for Bloop. And finally, because Bloop is able to work with all the build tools, with several build tools, we just have to write an integration for Bloop for that build tool. Those tools don't have to integrate with all the different build tools to be able to extract information about the build. They can just reuse Bloop that has information about the build. Also, having this centralized architecture, it enables us to get better optimization. Because Bloop has a full knowledge about what happens in the build graph, it's able to reason more efficiently about what needs to be written directly to disk, or if it can keep things in storage to avoid the cost of having to store stuff to disk. It's also able to perform better cache invalidation, knowing more about the build. And finally, because it knows everything that is going to be run, it can perform much better parallelization than our tools could. Moreover, because Bloop is going to share compilers between different clients, the compilers get more hot and more efficient. But what is that? We all know, I guess, that the JVM is going to optimize your code while it's running it. So that as the more you run the code, the faster it gets. And because every tool at the moment has a different instance of the compiler and nothing is shared, all the tools are going to be working to get a hot compiler instance. Also, at the moment with the tools that we have today, it's very easy to get rid of compiler. For instance, if you have the refactoring tool that gets a compiler, do some stuff with it, and just discard it, then the work that has been done to get the compiler hot is lost. With SBT also, for instance, whenever you do SBT reload, everything is going to be lost and you have to re-get the compiler hot to get a nice compilation performance. Another example is if you run twice SBT for the same build. You would compile the same code, but you would get two different instances of the compiler, nothing is going to be shared between the two. We've been running some benchmarks of hot versus cold compiler, and we have a link to the Grafana graph that show the compilation speed that's the benchmarks of the Scala C team at Lightband. And interestingly, you can see that the cold compilation performance can be up to 18 times slower compared to a hot compiler. And also, one more information that's important is that getting the compiler hot is very expensive because it will take time, it will take CPU cycles, it's going to consume lots of RAM, and finally it's going to drain the battery of your laptop. Alright, so let's move to how to actually use Bloop. Bloop is mainly a command line tool. So we've been trying to make sure that you get the snappier developer experience that you could get, so that you can use the shell that you have most likely already configured, so that it's nice to use for your usual workflow and you have all the tools that you're used to. And we've been working hard to get nice tab completion that is completely contextual to what you're doing. For instance, in the GIF here, you can see if you're trying to run the main classes of a project, Bloop is going to propose suggestions of classes that are runnable in your project. We have a configuration file for Bloop that we've been designing carefully so that it's very easy to read, easy to understand, and that can be read without the use of another tool. It's a JSON file. It's easy to read. First, you can see the name of the project, where to find the sources, the dependency of a project, how to compile it, that is the full class path, where to write the class file, Scala version, and so on. And as I've said, we've been very careful to make it transparent, easy to read and understand, and to have a full specification for it. Because the goal of that configuration file is that other tools can also be built on top of it and extract information about the build from this configuration file. Using it, you can, of course, interact with your build using either the command line interface of Bloop inside other scripts, or you can write more tools on top of that with the full specification that you can find here. We have the JSON schema. Okay. As I said, Bloop needs configuration file to be able to understand your build and how it's configured, what are the dependencies between projects, and so on. So someone needs to generate those files. And they're going to be generated not by hand because that would be really long and error-prone and boring also. The build tool is going to generate them. We have integration for several build tools, and you can just use them to generate the Bloop configuration file. So let's see how to get ready using Bloop. First, in the example of SBT, you would just add one SBT plugin, it's just one line. You depend on that plugin, and then using SBT, you can run Bloop install. And this task is going to generate all the different Bloop configuration files for a project. Once you have them, we expose 4 main commands for Bloop. First, we have Bloop compile, which obviously is going to compile a project and its dependency, doing it in parallel where it can. We have a very nice integration with file watches, so you can pass the watch flag, and Bloop is going to recompile a project whenever you change one of the source files. We have other integrations. We have several error reporters, so that you can pick the one that you find the most readable. And you can use help to get more information about all the options that Bloop compile supports. The second main command is Bloop test. This one is going to run the test for a project and its dependencies, but you can specify to run just the test for one of your projects with isolated, or you can select only a few classes or packages to run. For instance, in the command at the bottom of the slide, it's going to run the test for a project called frontend and only the tests that are in the package bloop.engine, and rerun the tests whenever one source file is changed. Then we have Bloop run, which is going to run a main class of your project. You can specify which one you want to run. You can use file watches again to rerun whenever the source files are modified. And lastly, one of the nice things that you get with Bloop being just a simple CLI tool is that you can use all the benefits from shell expansion that you have, and for which, in instance, in SBT, you would have to write a complicated task that would take care of collecting all the files whose name end with JPG inside an AMG directory. You get also the shell expansion for your home directory. Well, you don't have to write the SBT task to do that. You can use your shell as you're used to, just to pass that information to Bloop. The last command that you would use most likely every day is Bloop console. This one is the complete equivalent of SBT console. It just starts a new Scala REPL with your project on ClassPath and its dependencies so that you can test something quickly. All the commands that we have support intelligent tab completion in the sense that you get contextual information that is adapted for a project and the information about it. We have been very careful to have everything that is well documented with the help flag so that you get all the information you may want about one command. And finally, as I've said, you have access to the features of your shell. So you're in the best environment to be working efficiently. So let's do a quick demo of Bloop and how to get it set up. I guess that's big enough. So this is utest. It's a small testing library. So let's see how to get it configured for Bloop. So you go simply to the plugins.sbt, and you can add an SBT plugin. Whoops. So it's published in the CHCPFL Scala. The name of the plugin is SBT Bloop, and the version is 100M11. You can start SBT. And using Bloop install is going to generate all the source files, the configuration files. You can see it's very fast. Now you don't need SBT anymore. And using Bloop, you can check what are all the projects that exist. And you can finally compile. Maybe I can clean so that it's more interesting. So as you can see, the 3 projects are being compiled in parallel, which is, I think, very nice because we have this project has 3 different versions for Scala JVM, native, and JS. So everything can be compiled in parallel because there are no dependencies between them. Okay, it should be done soon. And once you've compiled, you can also run the test. Few warnings, and the tests are running in Bloop. So as you can see, it's very easy to set up Bloop. You just need to write one line new project to get started with Bloop, and then you can use SBT to generate all the configuration files.
I know what you're probably thinking. You're probably thinking, oh no, a new tool I need to learn. More a space of mind that you lose just by learning something new. Learning new tools is a frustrating experience, and I know that myself very well, even though I work on developer tools. So one of the things we wanted to do with Bloop is to avoid this problem. And the way we wanted to avoid it is by integrating directly with the build tools. You don't have to learn the new CLI that we just presented. That CLI is very powerful when you want to create custom extensions to your developer workflow at your company. But sometimes it's not just what you want. You want to get nice compilation performance by using the tools you've always used. This is the reason why we created Bloop in the first place, and to be honest, I think it's unfair if we ask you people here in the room to learn a new tool just to get better compilation performance. So what we wanted to do is to give the benefits of this tool to every developer, no matter what build tool they used, and therefore things like just making these improvements in SBT or just making these improvements to new build tools were not a solution, were not put on the table in the first place. So here's where I talk about the build server protocol. The build server protocol is a protocol that may be familiar if you've heard of the language server protocol. The language server protocol was created by Microsoft. It was first implemented in VS Code, and the problem that language server protocol was solving, or LSP in short, is to remove the duplication of integrations that were happening both in editors and language servers. So if you wanted to support your new programming language in an editor, you would need to replicate that support across all the different editors. And what the LSP did is to introduce the concept of a server in which the language server provided the language support for whatever programming language you wanted, and then the concept of client, in which would be the consumer of that support. And this allowed VS Code, VI, and a lot of editors that now implement this protocol to benefit, to automatically provide language support to them, right? So the difference here is that BSP gives us the same, but for build tools. It tries to formalize the communication between build tools and IDEs and editors as well. And the problem here is that most of the times build tools have information that is required for the simplest things like compiler diagnostics. Build tools are the source of truth because we define our projects there. So whatever we do in the editor or whatever our language support does needs also to get this information and operate on that. So in this case, clients are language servers and editors, and Bloop is the BSP server. And Bloop has been the first server that we have implemented in the build server protocol. This initiative has been a huge collaboration between the JetBrains team, Justin here, and myself and Olafur Paul Gerson at the Scala Center. We have just released, we have just announced the build server protocol 2 or 3 days ago, and there is now like a tweet that we just retweeted today. So if you want to learn more about that, you can just check the tweet out in the Scala Lang Twitter account. So I could be talking about the build server protocol for hours. So instead, what I'm going to do is I'm going to keep this brief, and I'm just going to say how this benefits Bloop. So the first thing is that it gives us fast project imports from IDEs and editors. So IDEs and editors need to import your project in order to understand it. We all know that when we use IntelliJ, for instance, we need to first import, or we need to reload the build when it changes. And what we want to achieve with the build server protocol is that we wanted to make this process as automatic as possible and as fast as possible as well. It is editor agnostic, as we said. So you could create like a BSP integration just to show, for instance, where the projects are defined in the project view of VI or Emacs, editors that don't usually have this kind of support. And it is also build tool agnostic, as we said before, and it provides you with better integrations with build tools that you may use or you may not, like SBT, Maven, Bazel, and whatnot. What this is important for is that we can use BSP to implement this kind of SBT integration, like this kind of build tool integration, built-in build tool integration that we were talking about. Bloop would be completely transparent to you. You would still benefit from it. It would be in the background, but you would not know about it, right? So what it will happen is that you will still use SBT or Maven, you will do compile there, and in the background, these build tools will connect as clients, ironically, to Bloop as a build server protocol, and Bloop will compile the code and then stream back any result that comes out of that. So if you want to learn more about this, you probably want to check out the talk that Justin and I did at the Scala Sphere 2018, 2 months ago. It's called Build Server Protocol and New Ideas. Or just check this link about the Scala Lang Globus that we were just talking about, in which we announced the first version of it. Here we can see a screenshot of what seems to be compiler diagnostics, warnings in this case. And here we see errors. This is a product of a prototype that I have been working on with Justin. And this prototype basically allows for a better integration between IntelliJ and BSP. So here, for instance, we have what happens to be, this GIF illustrates how we can achieve this fast project import we were talking about. So what we've done is that we were in the ACA project, right? And then we generate the configuration files, we do Bloop install. The configuration files are already persisted. And what we do is that we open IntelliJ. We wait for it, because the startup is a little bit slow, and then we say import project. Then we need to select the base directory of the project we want to import, in this case ACA. We say BSP, and we continue. And automatically, IntelliJ what it's doing now is that it's connecting to BSP on the background. It's getting all the information it wants, and now it's going to sync up. So it's going to get all the targets and going to show all the projects on the left sidebar. So as you see now, this is the actual sync. And we see that it's done in almost 6 seconds. So a process that usually takes around 2-3 minutes in normal projects with using SBT, and that can even take more when the first time you clone a project, is now taking about 15 seconds just by using BSP in the background. I think that this is a very nice improvement when it comes to developer ergonomics, because it means that whenever we change our build and the build and the IDE are out of sync, we can just immediately get those results in our IDE, and we don't need to wait and be blocked by all this expensive process that was being done before. Another example is a GIF that will show now how to get compiler diagnostics in the IDE. So what this is doing is that we are currently just removing a letter from a term, and we are compiling. So immediately we get the results in 2 seconds, and we get the compiler diagnostics that happen in BSP, happen via BSP in the build tool in our editor. So we can just click on them, and it goes directly to the place where they happened. And here we have a successful compilation, and here we have like a new change that will yield a compilation failure as well. I think this is especially important because, as you may know, IntelliJ uses its own presentation compiler to support Scala, and that does not always agree with the stock Scala compiler. So it has some glitches from time to time. You get some red squiggles, right? So what this will give you is the ability to know exactly whether the red squiggly is correct or not by just doing compile and seeing what happens.
I'd like to say a few words now about how fast Bloop is able to compare a project. So we've been trying Bloop on projects of different sizes. Okay. First we tried with the small to medium project. It's SBT, and we've been trying to compile it. It's about 50,000 lines of code, 20 modules, 800 source files. And using Bloop or SBT, you get immediately 25% better compilation speed. Then we tried on something that is slightly larger, 180,000 lines of code. It's the Guardian frontend, the source of the website. And we got, again, 28% compilation speed improvement. The next thing that we tried was Aka, which is, again, a large project this time. 330,000 lines of code, 36 modules, 1,100 source files. And we got, again, almost 20% speed up in compilation. The last project that we tried was Apache Spark, which is this one, a large project. It's 400,000 lines of code. And we got, again, 28% decrease in compilation speed. So if we plot that, this is a graph where the compilation speed is normalized compared to that of SBT. So one is always the compilation speed that SBT needs, the compilation time that SBT takes for your project, whereas the green bar here is how long Bloop took to compile it. And as you can see on the graph, you can be guaranteed to get almost 20% compilation speed improvement, whatever the size of the project is. And I think just by adding one line to our build SBT, being able to get 20% decrease in compilation speed is pretty nice.
So we've talked about Bloop. We've talked about how we can compile faster, how we try to remove the application, how we try to make your developer workflow faster, not just by compiling faster, but by integrating better with your IDEs and editors. But it's important that we just think about what's the future, what's ahead of us, what we want to do. Today, now I'm going to talk about two use cases that I'm most excited about. The first one is called remote compilation. Remote compilation is a process in which we compile our projects in the cloud and then we get the results back. Remote compilation is actually implemented by some build tools like Bazel and Pants, but they require architectural changes that are only possible in this kind of build tools. So it happens that if you use SBT, Maven, and Gradle and you don't plan to change that just because your developers have learned that tool from the beginning, you won't benefit from this powerful feature. And one of the good things about remote compilation is that your laptop can be active as your CI is running your tests or compiling. So that always keeps you busy. So as we say, in order to provide this kind of functionality, of course, we want to have hot compilers in the background compiling our code, and we want it to compile as fast as possible. But in order to do that, we need to get some cloud instances alive, some computers that are always alive and listening for requests, right? And the most problematic thing here is that in order to provide this feature to you, developers, we need to implement these two main changes, which are architectural. The first one is that compilation requests or compilation processes have to be completely independent. That means that they cannot even be sharing files, the same file system paths. And the second thing is that we need to be able to duplicate compilation requests. So given two compilation requests, I want to know if the second one is the same as the first one. And if it's the same, I just want to be streaming back the results. This is a change that we want to implement in the future, and I hope it will be available in a future release of Bloop. The second thing I want to talk about is pipeline compilation. Before I dive into the details of what pipeline compilation is, it's worth having a look at how we compile codes, how we compile our projects now. Traditionally, what we do is that we have a build graph, maybe sequential, maybe highly parallel, and this build graph is compiled by your build tool in two steps. There is first an ordering of all the build targets you want to compile. That ordering is usually topological, and then afterwards we compile them, allowing for a degree of parallelism that the build graph has. A normal kind of build graph is the one we present here. We see A as the root project, and then B, C depending on A, and then D depending on C. So what happens here is that in order to compile B and C, I need to wait for A, and in order to compile D, I need to wait for C. So pipeline compilation is a technique by which we can start a compilation of dependent modules before the compilation of A has finished. And we can do that by exploiting some properties of the compiler. In this case, they are called the Scala signatures that are generated after type checking. And we can use those and pass them around to whatever compiler instances that will compile B and C. So what that typically means is that we can start a compilation of B and C around 30-40% faster than before, because type checking a program usually takes around 60-70%. And the same goes for D. D can start even before that 30-40% faster, because the change aggregates. So it will start, it will multiply, speed up will multiply as the build graph grows. This idea was pitched in by Rory Graves at the Scala Sphere 2017. I remember hearing about it and being very excited about it. And there wasn't an implementation, so the first thing I tried to do is just to implement it myself. And I did a prototype in Zinc, the incremental compiler, and Bloop as well. This has high impact for any build graph. We don't yet have real-world results to assess how good it will perform in reality, but the theoretical performance speedups that we've said before keep us very optimistic about the consequences of such a change. The gains of this technique is a little bit constrained by the fact that you may have some Java code in your project. If you have Java code, then it means that the Java compiler needs to get the class files from either other Java projects or Scala projects. And therefore, you can only parallelize certain parts of your build graph instead of doing it for all of it. Thank you very much. Now it's time for the questions. So thank you for listening, and just feel free to ask us anything. Yeah, the question was how do you get BSP support in IntelliJ now, right? BSP has been merged in IntelliJ in the netlib of the Scala plugin, so you can just depend on it and upgrade to it from IntelliJ directly. You need to use IntelliJ EAP 2018-2. And the instructions are in the blog post I just linked here. You can just go to the Scala language blog post and you'll see everything there.
Yes?
Yep. During your talk, my battery went from 40% to 2%. You said that Bloop is a little kinder to the battery. Do you have any benchmarks for that? Your local development?
Not really, but let's say you could at least run more compilation cycles that you would do with SBT.
I think it would be interesting to try to find out a way we can benchmark this, but it would very much depend on your workflow and the way you use SBT, and if you keep SBT hot or not yourself. Like, it very much depends on lots of things. But by only having Bloop is only like an Nailgun server, so it only has one JVM, and it has the different compilers in different class orders. So that's better than just having IntelliJ have its own version of the compiler running in the background, optimized by JIT, and just your SBT shell doing the same, and potentially doing the same every time you reload or you exit. So there should theoretically be a big improvement just because of the centralization we talked about before.
I'm wondering whether this tool is able to help with to speed up dependency resolution when you add new dependency to the project.
The question is whether Bloop would be able to make dependency resolution faster. And the answer is that Bloop does not take care of dependency resolution by itself. When you generate the Bloop configuration files using Bloop install, SBT is going to do the dependency resolution, and then your class path is going to be exported to the Bloop configuration file.
Bloop does only 3 things well: compile, test, and run. Everything else goes to another build tool.
And it does only 3 things.
Have a good day.